What's going on, everybody? We've begun the process of learning about hypothesis testing, and now we're going to be exercising that new knowledge in the context of some statistical tests that you really already know. And we're going to begin with the z-test. So the z-test is something that involves the normal distribution. This will be very, very much like some of the exercises you've done in the past involving the normal distribution, but here, for the first time, we'll be doing them within the context of hypothesis testing. And we're actually also going to discuss an alternative methodology for hypothesis testing as well, as opposed to the traditional method which we introduced last time. So with that in mind, let's get ourselves ready here, and in particular, let's make it so that we are ready to receive some new information by clearing our minds of all of the things that get in the way of our full attention here. Let's make ourselves awake to the present moment, focus on our breathing, see if you can feel that your body is alive, make ourselves fully alert to what's going on in the now. Take some time for that. Welcome back. Well, let's first start off here with a review of what the steps are with hypothesis testing here. These steps involve, first of all, stating the hypothesis and identifying the claim. It's actually two hypotheses, aren't there? There's a null hypothesis as well as an alternative hypothesis. We've done some activities exercising that. The second step is to determine a test statistic, and guess what kind of test statistics we're going to be working with today? It's going to be z-tests. We're also going to work with some levels of significance, different levels of significance. Remember, that is our alpha value. Sometimes it's 0.1, sometimes it's 0.05, 0.01, 0.001, whatever it is. That test statistic and that level of significance really work together as far as determining what those critical values are beyond which we reject the null hypothesis. And that's what I'm talking about here. This is finding the critical values, computing the test value to see if it's more extreme than those critical values are. And then lastly, we make the decision to reject or not reject the null hypothesis. And then lastly, we just summarize the results there. Okay, so that's the hypothesis testing bit. Now let's also review a little bit of the z-test bit here. The z-test, it's a statistical test for the mean of a population. It can be used either when the sample size is larger than 30 or when the population is normally distributed, and most importantly, when the population standard deviation is known. The formula for the z-test here involves comparing the sample mean with the population mean and dividing that by the standard error of the mean, in which case we calculate this by the population standard deviation divided by the sample size here. And by the way, this population mean here is not known, it's hypothesized. So here's an example, and here we're going to be doing a z-test here, but we're going to be doing this in the context of hypothesis testing here. So a researcher believes that the mean age of medical doctors in a large hospital system is older than the average age of doctors in the United States, which is 46. So let's read that and start to ask the question, what is the null hypothesis and what is the alternative hypothesis? Let me read this again. Keep those two questions in mind here. A researcher believes that the mean age of medical doctors in a large hospital system is older than the average age of doctors in the United States, which is 46. So think of what those two hypotheses should be there. So assume the I'm not sure what's happening. I'm getting some strange music. I don't know where that's coming from. Oh, okay, it's gone now. Not sure what happened with my system there. That was kind of interesting. So assume the population standard deviation is 4.2 years. So we already know what that symbol is. That's the little sigma, isn't it? That's 4.2 years for the population standard deviation there. A random sample of 30 doctors from the system is selected, and the mean age of the sample is 48.6. So we know the sample size here now. That's n, which is 30 doctors, and we know the mean age of the sample to be 48.6. That's the x bar, isn't it? Right there. So we're going to test the claim with a level of significance alpha here at 0.05. Okay, remember, this is the probability of a type 1 error here. So this is going to be the sizes of those tails on the normal distribution here. Okay, so let's first of all start off with our hypotheses. Did you come up with some based upon this first sentence here? Hopefully you came up with the null hypothesis being that the average ages of the doctors in the hospital is the same as the average age of doctors in the United States, which is 46. That's the boring hypothesis. That's the nothing special is happening in here hypothesis. So, and that's the one that this researcher is hoping to reject with the statistical analysis. The claim that the researcher is making here, that's the alternative hypothesis, that it's actually larger than 46. So think to yourself, is this going to be a two-sided, two-tailed test, or is this going to be just a one-tailed test? Here's the test statistic here. It's going to be a z-test with this level of significance, alpha being 0.05. Okay, so the critical values then are going to have to be so it's actually going to look like this here. This is a z-test with alpha equals 0.05. It's going to be a one-sided right-tailed test here. And so as you can see, if I remove myself here, the size of this entire right tail over here is going to be 5%. That means that we're going to find whatever z value it is that has 95% of the area under the curve to the left of its value here. So z sub 0.95, whatever that is, as it turns out, this is our critical value here, so 1.65. So if we get a value for z with our z-test that is more extreme than 1.65, we're going to reject the null hypothesis. So let's see if that actually happens here. Here's the test value. Z is equal to 48.6 minus 46. So this is the value of the sample subtracted from the hypothesized population mean, which is 46. So that's according to the null hypothesis here. The hypothesized population mean is 46, so that's our value of mu. And we divide that by the population standard deviation divided by the square root of 30. Now this is kind of an important calculation step here. Make sure that you calculate this first before tackling any other part of this. So it's like calculate what this is first on the calculator and then like write that down someplace and then find out what this subtraction is, find out what that is, and then take that divided by whatever you got down here. Your calculator might not be as savvy as it needs to be when it comes to order of operations, and so the chances of misunderstanding as you enter this stuff into your calculator are very, very high. So to avoid any errors here, just calculate this first, find out what that is, write it down, calculate what this is, write it down, take this divided by this so you can get this. All right, so here's our test value. Z in this case is 3.39. Well, good grief, that's way off in Never Never Land, way over here, isn't it? It's certainly more extreme than 1.65. It's in the critical region. So the decision is that H0 is rejected. The null hypothesis is rejected. So to summarize, here's how we say this. There is enough evidence to support the claim that the average age of the doctors in the system is greater than the national average of 46. See, so that's how we report things as statisticians here. There's enough evidence to support the claim that the average age of the doctors in the system is greater than the national average of 46. Here's another example here. SAT tests. For a specific year, the average score on the SAT math test was 515. The variable is normally distributed. Oh, there's our z-test coming up here. So the population standard deviation is 100. The superintendent wishes to see if her students scored significantly below the national average on the test. So she randomly selected 36 student scores, and here they are. We're using this level of significance, so 0.10. Is there enough evidence to support the claim that the students didn't do as well as the national average? Okay, well, there's a couple of things we can extract from this. First of all, the sample size is 36. We can also extract the population standard deviation to be 100, as well as, and we can, I was going to get to this, after we add up all of these together and divide by 36, we get this for our sample mean. So 509 was their average score. That is below 515, but we don't know if it's statistically significant in its difference from 515 here. So we don't know if it's significantly lower than 515, low enough that we should really report that as an answer. So how do we do this? Let's list all of these sets of informations here. We have n is equal to 36. We have x bar equals 509. We have mu is equal to 515. The population standard deviation is 100. The alpha value, the level of significance, is 0.1. Here are our hypotheses. First of all, that the the average student score among all these students is 515, no different than the national average. That's not what this superintendent suspects is going on. She suspects that it was actually somewhat less than 515, so that's what's being investigated here. The test statistics for this is the z-test with this level of significance, alpha equals 0.1. So the critical values here are going to come from the fact that we are working again with a normal distribution, which I'll just draw over here for the moment. And the fact that this is specifically less than says that this is going to be a one-tailed test, a left-tailed test. So the test is going to be specifically over here. Here's our z-value. And it's going to be such that the area in this tail is the entirety of this alpha value, which is 0.1. So we're looking for the z-value where 10% of the data is to the left. Okay, so our critical value for that is negative 1.28. All right, so that's our critical value, so we know what the test is going to be like here. I think I'm going to have to erase this when I pull this up here. Yeah, let me quickly erase this. Okay, so here's our test value. Our z-value is going to be 509, that's our sample mean, subtracting off 515. So this is the difference between the sample mean and the theorized population mean. We're going to divide that by this standard error here, the population standard deviation divided by the square root of 36. Again, make sure you do this first on your calculator, write it down, find out what this is, write it down, take this divided by this to get your answer here. Negative 0.36. Interesting. Well, that's not more extreme than the critical value here. So even though we're seeing a slight we're seeing a difference in the average here being less than 515. It's not enough of a difference to specifically conclude with any level of certainty that the average among the students is anything different than 515. So it's not significant in its difference. So the summary of this is that insufficient evidence exists to support the claim that the students scored below the national average. And by this I mean students as a whole, that all of the students, not just the 36 ones that were sampled here, certainly the 36 who were sampled here scored below the national average, but we're talking about all of the students. So there's insufficient evidence to say that the students, all of the students, scored below the national average. All right, here's another one. Ooh, that shouldn't say SAT tests. This is rehabilitation costs. Okay. The Medical Rehabilitation Education Foundation reports that the average cost of rehab for stroke victims is $24,672. It's amazing. To see if the average cost of rehabilitation is different at a particular hospital, a researcher selects a random sample of 35 stroke victims at the hospital and finds that the average cost of their rehabilitation is $26,343. Okay, so that is bigger than the national average. The question is it significantly bigger? The standard deviation of the population is $3,251. We are examining this with a pretty low alpha value here, 0.01. And so with this level of significance, can it be concluded that the average cost of stroke rehabilitation at a particular hospital is different from the average cost presumably around the country? So here's a problem very much like what we did before. Think about what those hypotheses are. Think about what the statistical test is going to be, what those critical values are going to be, what kind of a test is this going to be? Is it a two-tailed test or a one-tailed test? Which side is it if it's one-tailed? And compute whether or not what the z-value is and see if it warrants a rejection of the null hypothesis. It's a lot of work ahead of you. Take some time to do this. Welcome back. Well, hopefully you're starting to see that the procedure for doing this is fairly consistent. I mean, we're starting off with the hypotheses. We follow that up with a test statistic and a critical value determination of what we're going to be doing here. We decide what our critical values are based upon the nature of the test statistic and the value of the critical value here. We get those critical, this is the level of significance, I should say. We get those critical values. We figure out what our test value is here, and we're comparing our test value against those critical values to see if this is more extreme. And since it is more extreme than these, we decide to reject the null hypothesis here. And again, the null hypothesis is that this is just a slightly above the average and doesn't really reflect a significant difference here. But in this case, it's extreme enough of a difference here based upon what we know about the population standard deviation and stuff like that, that we have sufficient information to reject the null hypothesis. So there is sufficient evidence to support the claim that the average cost of rehabilitation is larger at this particular hospital. Okay, so that's the traditional way of doing hypothesis testing. There's one additional method here that we'll show you, and it's called the P-value method for hypothesis testing. It's almost exactly like the traditional method, except it's got a slightly different way of describing some things here. The P-value is the probability of getting a sample statistic or a more extreme sample statistic in the direction of the alternative hypothesis when the null hypothesis is true. And that's some $10 language there that basically says if you find out that your test statistic is here, such that only 1% of the curve is beyond this, then your p-value is 1%. If your test statistic is at this point here, well, let's say this point here, where the area of the curve beyond this is 5%, then your p-value is 5%. If this is a two-tailed test, then, and let's say you get a test statistic that's out here, then you have to take this area out here plus this area out here to find out what your p-value is. Basically, the p-value is the probability of getting a test statistic that's more extreme than what you've got. See, so that's essentially what it is. So the goal is when you, as a scientist, and I've watched the looks on scientists' faces many, many times, you really want that p-value to be small, 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 small. And when it gets below 0.05, there's a smile on the face. If it's below 0.01, boy, they're really smiling. If it's below 0.001, they're really, really smiling. That basically says that the chances of a type 1 error here are very, very small. You really have almost certainly found something that is of significance to report. So let me erase my little drawing here so that we can go through this. So once again, we state the hypotheses and identify the claim that's precisely the same as before. We determine a test statistic and a level of significance. Again, no change from before. We compute the test value and find the p-value. All right, it's just one extra step here from the test value. And then we make the decision to reject or not reject the null hypothesis based on the size of this p-value. And then lastly, we summarize the results. So as you can see, it's almost precisely the same as before here. I mean, it's just a slight little tweak here, but this is actually pretty common in our method of hypothesis testing here. So it's good to know this. Cost of college tuition here. A researcher wishes to test the claim that the average cost of tuition and fees at a four-year public college is greater than $5,700. Boy, we wish. That would be really, really nice, wouldn't it? To be just $5,700. She selects a random sample of 36 four-year public colleges and finds the mean to be 5950. Okay, which is above 5,700. We'll see if it's significantly above 5,700. The population standard deviation is $659. Is there evidence to support the claim at an alpha level of 0.05? So this looks very similar to our previous hypothesis testing methods, and in fact, it's going to look like that as we're sketching this out here, but we're using the p-value method, so you're about to see something slightly different about 2/3 of the way through here. Our hypotheses are exactly the same as you would create before. Our null hypothesis is that there's no difference from the national average here, or what we think it is, $5,700. The alternative hypothesis is that the average is larger than 5,700. In particular, she's looking for the possibility that it's greater. So this is going to be a one-tailed test. Determine a test statistic and a level of significance. This is going to be a right-tailed test because this is greater than 5,700 with alpha equals 0.05. You want to compute the test value. Again, this is going to be a z-test here. So z is equal to 5,950 minus 5,700, so the difference between these two things, and we'll divide that by 659, that's the population standard deviation, divided by the square root of 36. So again, do this separately on your calculator, write it down, do this separately on your calculator, write it down, take this divided by this to get your answer here. So our z value is positive, which makes sense. This is larger than this, so it should be in the positive part of the normal distribution, and more specifically it's 2.28, and the probability of getting a z value more extreme than that is 0.0113. How do you figure this out here? The probability of getting one that's more extreme than that, that's the complement of whatever you get for this. You can look this up on the table, can't you? All right, so I'm guessing that when you look this up on the table, what you get is 0.9887. Because when you are finding this, you take 1 minus this, to find out what its complement is. It's because we're finding out the probability that you get a z value that's greater than 2.28 instead of less than 2.28. It's always, you're looking at getting a z value that's more extreme than the one before. And if this is negative, that means we want to see what's the probability we could get one that's more negative. Okay, let me erase this. And then, based on this, we make the decision, summarize the results. We reject the null hypothesis because this p-value here is less than 0.05. That's the only difference here. Everything else is exactly the same here. So H0 is rejected because there is sufficient evidence to support the claim that colleges cost more than $5,700. And here's the p-value. It's less than 0.05, so that's why we are rejecting the null hypothesis. So we're looking at this p-value rather than comparing the statistic here with some critical values. That's the only difference. All right, so try this one using the p-value approach here. Everything else is going to be pretty much the same. Just make it so that after you calculate your z value, find out the probability of getting a z value that's more extreme than that. Once you've got that p-value, compare it to your alpha value to see if you should reject the null hypothesis. Take some time for that. Welcome back. Well, my apologies. I think I left off an important piece of information on here, so the results as they stand right now might look a little confusing. The reason why H naught is not rejected here is because this is a two-tailed test, and so we've got this area here that is to the right of 1.89. Let me actually draw this here out so that it's a little more clear. 0, 1.89, and so the area of this tail right here is 0.0294, and if that's all we were working with, then yeah, that would be less than 0.05, and so we would reject the null hypothesis. The thing is that this is a two-tailed test, and so we also have to consider the other side here, which has a tail that is exactly the same length there, 0.0294. So we have to add these two things together. 0.0294, 0294, that's going to be 819.0598. So our p-value here is 0.0598. It's twice as big as this, and 0.0598 is larger than this alpha value of 0.05, so we don't reject the null hypothesis. All right, so in doing this, we're just combining some things that you already know how to do, and we're just putting them together essentially. So do you know how to perform a z-test with the mean using traditional hypothesis testing? That's where you created those critical values, those critical z-values, to see if you get something that's more extreme than that. And then we have the alternative approach here using the p-value method. That's where you find out where your test statistic lies, and then you see what is the probability of getting a z-score that is more extreme than what you got, and that's your p-value. In both cases, you're comparing that against an alpha value that's given to you for the level of significance. So hopefully that's sufficient enough for you as far as working on the assignment. This is some pretty cool stuff and very widely used in the industry. So hopefully this will be straightforward for you with the assignment, and I'll see you in class.